Good to go. All right, howdy. Hey friends. So let's take a look at that integral on the whiteboard. So if I gave this to you and asked you to do it, what are the options? Option one would be go find the table. I've got that new sweet, like the greatest table ever created, which I'm sure I ranted about on Wednesday. In the content area, and I highly recommend checking that thing out and getting yourself a copy of it. Just download that. I could go to that table and try to figure out which of those forms this best matched, and then excuse me, knock it out. The other option is I could notice that the denominator is a polynomial. And more importantly, a polynomial I can factor, and hopefully you can too, or at least have a sense of where to go with that, or got an inkling that, yeah, that thing could be factored. So let's write that down here then. Okay, well, hey, let's do that. Let's factor it up. So I'm just going to keep it in integral form for the time being. So I've got this, and then that's just the difference of two squares. So x minus 3, x plus 3. Cool. Now, at this point, we don't really have a way to do this. There's no substitution that's going to work. And actually, here, real quick, let's just go back to the original. That probably should have been something we considered when we see any integral. Does substitution work here? So if we did that, we'd probably be shooting for this form here. And you can see that if I let u equal x squared minus 9, then du is going to be 2x dx. And I'm missing this essential variable in the integral. If there was an x dx on top there, got it. It's a natural log form, but it's not, so not going to roll. So let's back out of here. So the technique we're going to talk about today is called the method of partial fractions. And this method is useful when you have a polynomial denominator that you can factor. So 0.2 right there. And there's a new web work that's going to be open today, Friday, the whatever, and Friday the 9th, I guess. And the first 4 problems in that set are partial fractions problems. So give those a chance to stew in your brain before Monday, or maybe just completely knock them out. But let's talk about how to approach them. So let's go back to the problem at hand. I've got this integral, which really, it's this fraction. These are called rational functions. When you have a polynomial over a polynomial, that's called a rational function. And I'm just doing something kind of silly, but to point out that this thing here is the fraction that I want to do something with. And what that something is to break it into a sum of simpler rational functions. And then hopefully each one of those I can either knock out with a simple substitution, maybe even in my head, or I can access a table if something's really horrible looking there. But that's not going to be the case for the first 4 on the web work 3. So here's the plan, the method. Let's keep it in blue over here. Here's the method. Step 1 is the setup. And what we're going to do is decompose the integrand thing, the function that we're integrating. And this is actually can get very complicated and very elaborate. And there's lots of little subtleties that we could go into, and we are not going to go into. We're really only going to take a couple of basic cases to deal with so that you're aware of this method. And then, later on, if you wanted, you could go expand and deepen your knowledge. So the setup here is I take my polynomial rational function, and I actually need to have that denominator factored for this to work. And there's a couple other caveats that we'll talk about in a minute. But the setup is, what could this have come from in terms of the sum of some other things? And think about how you add fractions together. If you had two fractions, one that looked like this, and there's some number on top, and one that looked like this, with a different, potentially, number on top, and then you added these. So just take a look at this and think about the process of adding those two fractions together. What's step one? Well, get a common denominator. And here the common denominator means I'm going to multiply this first fraction by x plus 3 over x plus 3, and then this fraction here I'm going to multiply by x minus 3 over x minus 3. But the common denominator I'm shooting for is the denominator I started with. So I'm just trying to explain the rationale for that decomposition. Excuse me. pretty congested today. So the setup is, take your rational function and write it as the simplest rational functions with variables on top. Because I don't know what numbers a and b are going to work to get me a 1 when I add these up. Let me even do this a little bit more. What if I had like 2 over x minus 3 plus negative 1 over x plus 3? Well, let's add those together so you can just kind of see how this works. So this first one, I'm going to multiply by x plus 3 over x plus 3. So it's going to be 2 times x plus 3 over x plus 3, x minus 3. And then this second one, I've got the negative 1. I'm going to multiply by x minus 3 on the top and the bottom. And that's going to give me the same denominator as the first one, which was the point. And then adding these all together, or just doing the simplification. Now we've got our common denominator, so we can put that underneath a big bar. And then 2 times x plus 3 is 2x plus 6. Negative 1 times x minus 3 is negative x plus 3. And when I simplify, we're going to get x plus 9 over x plus 3, x minus 3, which is not the thing that we started with. So clearly, a is not going to equal 2 and b is not going to equal negative 1. And instead of just guessing all day and trying these out and figuring out what a and b should be, we've got a method for finding them. And that is the method of partial fractions, step one of which is this general decomposition stage in part 1. Now you can pause this video at any point you need to. I'm going to roll on with the method. So let me just kind of get here again. We have the setup, which is writing the fraction of interest. And in its most general decomposed form. Step 2 is going to be clear out the fractions. So I'm literally going to just multiply through by the original denominator. So here I'm going to multiply through by x plus 3 and x minus 3. Again, getting rid of all the fractions is an important step in this process. So when I multiply the left-hand side, I just get 1. When I take that left-hand side, which is my original fraction, I'll always just end up with the original numerator. And then equals a times the x plus 3's would cancel, so I'm left with an x minus 3, plus b times the x minus 3's cancel, leaving me with an x plus 3 there. And so then we've got 1 equals ax minus, so I'm gonna simplify this down now and multiply out the right-hand side. 3a plus bx plus 3b. And let's group together like terms now. So this is actually 1 equals a plus b times x plus, and then the constant terms are going to be 3b minus 3a. So at this point, I've got a system that I've created. In other words, I understand that a plus b has to equal 0, and 3b minus 3a has to equal, did I do this all right? Yep, has to equal 1. There's no x on the left-hand side, so a plus b has to become 0. And then the other term has to become the constant that I see in front of me. So now I could go through and solve this system of equations. Lots of ways to do that. You could take this first one, which says that a is equal to negative b, and then plug that into this equation. In other words, replace a with negative b. And what you'd get is, so I'm replacing a with negative b there, equals 1. And so check it out. Now I've got 6b equals 1, b equals 1/6. And since a is the opposite of b, I've got a must equal negative 1/6. And so now at this point, I'm done. That's my decomposition. I now know that 1 over x plus 3 times x minus 3 is equal to negative 1/6 x plus 3 plus positive 1/6 x minus 3. Now check it out. This actually makes my original integral, which looked like this. Oh, I got to remember which one had the negative. So it was, okay. So this is now equal to negative 1/6 over x plus 3 plus 1/6 over x minus 3. And each one of those is a natural log form. And the u and the du and the dx are actually going to be equivalent, right? You're going to, in this first one, you're going to let u equal x plus 3, and then in this one you'd let u equal x minus 3, and you can see that du is equal to dx. So actually pretty straightforward, and we're just going to go right to that natural log form. And my next step then is that this is equal to negative 1/6 log of x plus 3 plus 1/6 log of x minus 3 plus c. Done. Right? Not bad. There's fancy things I could do with these logs if I wanted to, but try to keep things nice and tight today, not kind of get off and have my math jollies. So that looks beautiful. Let me show you another way to approach finding that a and b in the original system. So I'm just going to back up here real quick and look at that. Let's see. So, okay. Yeah. So at step 2, this is where I'm going to pick back up. I want to show you another way to approach things once you get to step 2. So remember that this was our original setup. And I flattened it out by multiplying through by the original denominator. And I think you're going to like this. No system solving needed here. If I let, now this has to be true for all x values. We want this thing at the top to be true no matter what x is. In the top form, I can't let x be negative 3 or positive 3 because then I got division by 0. But I don't have fractions anymore. So check this out. If I come down here and I substitute these originally explosive values into this equation, what do I get? So if x is equal to 3, then I get 1 equals a times 0, a dies, plus 6b. And check out what that tells me. B is equal to 1/6. Not bad. Then the other, what is the other awesome value I could pick? Just take a second. What is that awesome value? There's one other one. If you said x equals -3, you are correct, because that's going to kill off this b term here. So if I let x equal -3, I've got 1 equals -6a, and the b dies. So that gives me immediately a equals -1/6. And I get to the same place with way less work. I would recommend this method when it can work. And it's not always going to work. Sometimes things are going to get a little bit messier. Maybe even today. I'm looking at the clock. Yeah, they're going to get a little messier. So that's the original setup. Let me give you one to try. So what I would like you to do is work this one out. Let's find the integral of sorry, I had some problems written down. I can't find any of them. Where the hell are they? Well, shit, I guess we're just going to make one up. So this one is going to be 2 over x squared minus 4 dx. We'll just start out chill. And then maybe right now, pause the video. We can do this with this format. Pause the video, work this through, come back. And I'm going to work it through right now. But if you don't work it through, you're not getting the full benefit of this. And do as you see fit. So, set up. Okay, pause. Now we're back. Okay. So, set up. I recognize that's the difference of two squares, and that this denominator, which I should have factored over here, looks like that. Clear it all out, multiply through by x minus 2 times x plus 2, and I get 2 equals a times x plus 2 plus b times x minus 2. Now I'm going to pick values. I'm going to let x equal positive 2, and that's going to kill off the b. So 2 is equal to 4a. And so a must equal a half. And then I'm going to let x equal -2. And I've got 2 equals, this time the a dies off because -2 plus 2 is 0. And we've got -4b. So b is equal to -1/2. And we're done. Now we rewrite this integral. We've got, this is equal to our new problem. And so our new problem looks like this. 1/2 over x minus 2. And let's just put the minus there. Minus 1/2 over x plus 2. Whew. Sorry. Yes, I'm actually, like, this math is tiring me. It's making my voice a little rough. Again, natural log forms. Natural log forms are something I would be looking for in these problems a lot. And hopefully you can just agree with me. Well, you don't, no, I mean, I don't want you to just agree with me, but hopefully you can believe and understand that that is our final answer. Again, avoiding the jollies that I see before me, a cornucopia of fun log things to do. We shan't do them. Okay, cool. So if you got that, awesome job. If you didn't do it, I don't know, you didn't do anything, so I can't really like give you kudos. I can give you hope. I can share my hope with you that the next time we do this, which is going to be in just a few minutes, you'll play along and you'll get so much more out of this. It's going to make the web work easier. So next example. What about this guy? Okay, kind of like our original. Kind of, but not totally. So for this one, yeah, I was like, now I'm like doubting myself. There's no way I'm freaking recording this all over again. I'm gonna back off. I'm gonna back off just 1 second. I'm gonna do something just slightly different. I'm gonna work this one through. So let's just take X. Now, what just changed there? There actually is something to learn. The original problem I had written with the X cubed, the degree of the numerator was greater than the degree of the denominator. So one of the things I want to point out here is that the method of partial fractions only works when the degree of the numerator is strictly less than the degree of the denominator. However you spell that, I don't know. That looks pretty bad. That word is denominator. That is not the case here, but the minute I put that x cubed, or even if I went to x squared here, all goes to hell, and I can't use this method without doing something else first. So let's do this one with our standard method. So I've got the same denominator. I've already done the factoring, and the setup's the same, even though there's an x on top. Now you might want to actually pause and see if you can work this through, because I'm about to. It's a good practice run. When I flatten this out, I'm going to get, notice then there's an x now on the left. It's a variable this time as opposed to a constant. Ta-da. So let's let x be our special values. So those special values are the same as they were before. Still magical. This time when x is 3, I'll kill off the b. So I've got 3 on the left. So notice that the left side will change depending on the variable or the value I plug in for x. So then I've got 3 equals 6a, and a equals a half, and then I'm going to let x equal -3. And I've got -3 equals -6b. And so b equals a positive a half as well. And my decomposition then is integral of 1/2 over x minus 3 plus 1/2 over x plus 3 dx. And you can always check this. You can, you can kind of maybe quickly in your head do the sum of these two fractions, and you can see that you're going to get a 1/2 x and a 1/2 x, and that's going to give you the 1x, and you're going to get a 3/2 and a -3/2, and they're going to cancel, and that's going to make the top just perfect. And so then, we got good old natural log form here. Done. All right, let's go to that next case with the larger numerator. So we started like this, and I'm just I am going to leave the bottom unfactored. So I can't use partial fractions because the degree of the numerator is 3, degree of the denominator is 2. So what I have to do first is long division of polynomials. This is something I guess I pretty much enjoy almost everything we do in our class. So I like this. Hopefully you've seen this somewhere along the way. If not, I'll pop up a video on this. I'll add this to the class so that you can, refresh on how to do this, but I'm going to go through it right now. So step 1 here, I'll call it step 0, is use long division to simplify first. Now, and long division doesn't want the bottom to be factored. I know that I can factor the bottom, but for this part of the process, leave the denominator unfactored. And how are we going to do this? So we are going to divide x squared plus 0x minus 9 into x cubed. Notice how I put that 0x in there. You want to put placeholders in. And this is something, that gets done with long division of numerals as well. You put in placeholders when you need them. And it's super important with these polynomials. So whatever I had here, like for example, if this top had been x cubed plus 3, I'm clearly stuck on 3s, I would have to put plus 0x squared plus 0x plus 3 under here to keep all those little ducks in a row. But we aren't going to do that. Instead, I'm just going to put normal placeholders in there. It might help. I originally I wasn't going to do this. Let's just put that shit in there. This video now became like not fit for children on YouTube. Oops. So long division, always look at the leading term on your divisor and move across the thing you're dividing into. When the name is escaping me. So x squared into x cubed. What do I have to multiply x squared by to get x cubed? And the answer is x. So that's the first part of my answer. Now I take x times this entire thing and put it underneath. And what I'm going to get is x cubed plus 0x squared minus 9x. Notice how what I've got here is just this thing on the left times x. And I'm going to subtract down, and these are going to cancel. And that was the point. I'm only focused on that first term and getting that to work out. And then everything else kind of just keeps, it's like, when you're trying to get a wrinkle out of a blanket, we're just working on this part and we're pushing down and hoping to get it out. But we work on one spot at a time and push the rest to the right. So here I'm going to subtract. And when I do that, I get 0x cubed, 0x squared, and then positive 9x. So now I'm done, actually, because x squared doesn't go into 9x. If that had been 9x squared, then I would have, it would have been times 9 would have gotten me into that, but it's not. So I'm done. And let's see here. So when I subtract down, let's see, we got that, and bring this guy down. It's bringing down that plus 0. If there was something else there, I would also want to bring that down. So if that had been that minus 3 or plus 3 I had at the beginning, I would have brought that beast down as well. This is my remainder. And what it means is I've got 9x over x squared minus 9 left over after I divide and get the x out. Now that just sounded like a bunch of garbage. Let me write this out. So in other words, what I have now is integral of x plus 9x over x squared minus 9 dx. Yep, that's it. So now, what does that mean? Let's just do a quick check here. If this thing here, if you were to actually add these together, and I like to do these things backwards and forwards a few times just to show you that everything is totally kosher. If I had to add these two things together, I would first have to get a common denominator. Whoa, got a little crazy there. That common denominator would be x squared minus 9. So I'd take this person here and multiply by x squared minus 9 over x squared minus 9. And when I get done with this, check it out. I'm going to get x cubed minus 9x plus 9x, and I get back the original thing that I started with. So it's all good. I was like starting to sweat it there. It's like, well, did COVID rot my brain more than it already feels like it did? Luckily, it didn't hit this math cell. So now I've got this new problem. Take a look at this problem. Do I need partial fractions? What are the methods that we know of so far? Table. No, don't think about table now, but the table's going to be one of the things. It's usually like the last resort. It's the most desperate move we have in our class. I have substitution. Does substitution work here? Because if it does, I don't need to go to the partial fractions. I could, but I don't need to. So what do we got here? Take a moment and see if you can actually work this integral through. Pause. I'm restarting. So I'm going to work this through, and I can see that the antiderivative of x is just 1/2 x squared. So that part's easy. And then I'm going to leave this integral, which is really the heart of our work, to do. And turns out that's just a natural log form. Notice that if you let u equal x squared minus 9, du is 2x. So dx. So dx is going to be du over 2. I'm going to erase all this stuff. Like convincing you that, trying to convince you this worked. And then I'm going to rewrite this integral. So this is equal to, carrying along what we've done, bring that 9 out in front. And then I've got x over, I make my substitution, u, and then dx is du over 2x. Forgot to bring that x underneath there too. So there's 2x. That would have been bad because the x's wouldn't have canceled. And you see that they do now cancel. Boom, boom. And we've got 1/2 x squared plus 9 times 9/2 integral du over u. That's 1/2 x squared plus 9/2 log u. And I'll wait on the plus c because I want to back substitute. And I've got 1/2 x squared plus 9/2 log absolute value of x squared minus 9 plus c. It's a lot of work. But we got it. We done it. Good work, my friends. And just good work staying and making it through this far. I appreciate your company. Some part of me, some ethereal part of me knows you're watching this right now, and it's helping me just heal and be a better person and all sorts of other shit. So, all right, now, next. What do we got on my plate here? Oh, Lord, let's look at the last little trick we need to talk about. So this last little trick is, let's say I have an integral like this. Notice that the bottom is completely factored, and it consists of a repeated factor. It's just x minus 1 times x minus 1 times x minus 1. So this is the repeated factor case that I want to talk about. If you have a repeated factor, where could that fraction have come from? So again, we're doing the same game. Decompose the fraction into simpler fractions whose sum is the original. So here we have to go for the most generality. Now, I could have an a over x minus 1 cubed, but all of the fractions I'm about to write, if I added these together, the common denominator would be my original denominator. So check that out. This fraction on the left, the x over x minus 1 cubed, could have come from this sum, and I have to allow for that sum because it's going to turn out that a, b, and c are not all going to be, well, they're not all going to be 0. Clearly, if they were all 0, we'd have a real mess here. Also note that the degree of the denominator is 3. The degree of the numerator is 1. So totally kosher in using partial fractions. But when you have a repeated factor like this, you have to do the setup accounting for each of the lower powers of that factor. I mean, thank God that wasn't x minus 1 to the 5th, because if it did, I'd have 5 separate fractions for the 5th power, 4th power, 3rd, 2nd, and 1st. We don't have that. So in partial fractions, like one of the things you study is like how to do these original setups. If you take differential equations in the spring, and I'll be teaching that, we will really get into this, like way more than this. It won't be just like, an hour lecture. It'll be like a week or something like that. So please still come, even if you're like, that doesn't sound that great. All right, so this is the setup. And let's do the flattening. So I'm going to multiply through by x minus 1 cubed. And when I do that, the left side just becomes x. And then I've got a completely cancels, plus b times, I'm left with an x minus 1, the first power. And then when I multiply through on the c term, I get c times x minus 1 squared. All right, doesn't look too bad, right? Nice, everything's all factored and pretty. Let's play our game where we pick special values. What are the special values that I should use here? Take a minute and think about it while I sip my tea. If you said x equals 1, you are right, because we're looking for the things that kill off terms on the right-hand side. So let's go, let x equal 1. And then what does this expression become? 1 equals a. Oh, shit, we did it. Luckily, I marked this video kiddo unfriendly because I just can't stop cussing, apparently. But it's because I'm so excited that it was really easy to get A. So we already know what the A is going to be. It's going to be 1. Now, what about B and C? Things get a little trickier here because there's no more good values to pick. So at this point, we're just going to pick other values. And we're going to go for the low-hanging fruit, right? So if this is the tree of all great values, there's pi, and then there's e in there, and oh shit, there's imaginary number in there on the ground under that tree. For us, there are some really sweet values for partial fractions, and letting x equal 0, 1, or -1. Can't go wrong with those. They're really lovely to work with. So we've already used 1. Let's go for x equals 0. So I'm just going to let x equal 0. And when x equals 0, I've got 0 equals a plus b times 0 minus 1 plus c times 0 minus 1 squared. And now I got to work this through. I already know a equals 1, so I could come in there, and I'll do it on the next pass. I'm going to replace a with 1. So I've got 0 equals 1 minus b plus c. So I've got this new equation that says, and I like to put all my constants on one side with my equations. So I've got negative B plus C equals -1. All right, let's pick the other value, the other one from the ground over here. Grab that one. Oh, joyous -1. But wait, whoa. There might be one other value to pick. It's like -1 can go risky. What would be another good value to pick? It's up here on a branch. There's like a branch up here on the tree. What number is up there? The tree is handing to us. That would make that equation pretty. Look at the terms. What x value would make things pretty? The answer is x equals 2, and that's what I'm going to go for. So x equals 2, we have 2 equals a plus b times 2 minus 1 plus c times 2 minus 1 squared. See how nice that is? Yeah, because 2 minus 1 is 1. So I'm still low-hanging fruit valuing this whole thing. So we've got 2 equals 1, which is a, plus b plus c. And yeah, so what this tells me is that b plus c equals 1. Now I've got a system of equations. I'm sorry, tree of kind values. Be gone. So let's write these two equations. I've got these two things right now, and I need to solve them simultaneously for b and c. So we've got -b plus c equals -1, and I've got b plus c equals +1. And this is a nice thing. I can just add straight down. If I add straight down, I get the b's canceling. 2c equals 0, so c must be 0. Woohoo! Outstanding. C is 0. So if c is 0, plug that back into either one of these, you can see that b must be +1. And we're done. We have our decomposition. A is 1, B is 1, and C is 0. So I'm going to flip the page if you want to pause and think about that for a second, because I'm going to finish this up. So this is the last thing we're going to do for today. So what did this turn into? It was 1 over x minus 1 cubed. And then I've already forgotten. B was 1. And then C was 0. Yeah, sorry, I'm just thinking, I was like looking at this and like, that's so nice. That's too nice, but it's true. So I'm just going to go with it. And that's our new integral. And these are just use substitution power rules. This is x minus 1 to the -3rd. And this is x minus 1 to the -2nd. And if I let u equal x minus 1, du is dx, it's all beautiful. And so I can just power rule, right? This becomes so back substitute, and I'm done. Good. Hope that works good. One last note, had this original integral had some limits on it, like this, I would just go through this process, use my antiderivative that I just cranked out. So in other words, I just did it, it's right there. So it's do that from 2 to 3, plug and chug and simplify, and I'm not going to do it. Just wanted to make that note. So my friends, let's see, I think that was a pretty good, I don't have a little timer here on the thing, but it's probably enough for everybody, right? So first 4 problems on web work, you should actually totally be able to knock those out now by Monday. Give that a shot. On Monday, we're gonna keep practicing this stuff and maybe add some stuff. We'll definitely add some stuff about tables in, and also I want to talk about hyperbolic trigonometric functions, just so you're aware of what those are. Probably like ring some ancient bells, you know. You might have heard them some other time, but we're gonna add that to our bank of things that functions that we understand and know how to integrate. So that's it for today. Thanks for being here, and I really look forward to being back in shape and with you all in person on Monday. So be well, my friends. See you soon. Bye.